Hello and welcome. In this video, we're going to be taking a look at the notes for kinematics in one dimension. Remember to try each part, pause and rewind the video as necessary, and when you come to a section that says test your understanding, please give it a try, okay? And then follow along with the video to see how you did. Don't do any of the examples, well, I mean, unless of course you really want to, because those are things we're going to be doing in class. Introduction Chapter, Section 5, Vector and Scalar Quantities. What is a scalar? A scalar is a quantity that has magnitude only. Explain what a vector is. A vector is a quantity that has magnitude and direction. The word magnitude refers to the amount of something. So explain what the word magnitude means. Well, as stated, it means amount, but it could also mean size or quantity. Essentially, magnitude is the number value of the problem. It's the number amount. Section 1.1, what is motion? Explain in your own words what the object of interest and the observer are when describing motion. The object of interest is what is being observed. The observer notices the object. So with that, let's take a look at the following riddle. Is it possible for an object to be both moving and not moving? Well, the short answer to this is yes, it is possible. I want you to refer to Observational Experiments 1.1 and 1.2 in Section 1.1 of the electronic textbook. It is possible to be moving and not moving simply because it depends on this thing called the frame of reference. Now, you might hear me refer to it as a frame of reference or a reference frame. Both terms are used synonymously. So yes, it is possible to be moving and not moving because it all depends on a frame of reference. Because again, all motion is relative. Explain in your own words the statement motion is relative. Well, the phrase motion is relative basically states that the motion of an object depends on the observer's point of view. Explain what a reference frame is in terms that a junior high student can understand. Reference frames are things we need to begin any problem. We really cannot establish a problem without one. Reference frames establish a beginning structure to the problem. They also define one possible reality within the problem too. A reference frame is a set of standards that we give any problem in order to begin the problem. Now, a reference frame must include the following. It must include some object, some point of origin where the problem is starting, and then some way to measure this time. Please take a second to get all of this down. Reference frames, again, are important because we cannot establish a basic reality of the problem without it, especially if there are multiple objects existing in the reference frame, because again, motion is relative. So let's examine the following riddle. A police officer stops a person for going 70 miles per hour in a school zone. Pretty fast in general, much less a school zone. In any event, the driver claims that the car wasn't moving at all. Explain how both can be correct in physics. Use the vocabulary you've already learned in this section in your answer. Well, you have two objects in this reference frame, the police officer and the driver. So, according to the police officer, the driver is in a moving car and therefore was moving 70 miles per hour and therefore was speeding. Now, according to the driver, the inside of the car appears to be motionless. So, from the police officer's point of view, you have a moving car that's going 70 miles per hour and a driver who's inside this moving car. Therefore, the driver is also going 70 miles per hour. However, according to the driver, if the inside of the car appears to be motionless, not moving, then it stands to reason that from the point of view of the driver, if you're not moving, you cannot very well be speeding either. Obviously, the police officer is going to win this one in a court of law. Define linear motion in terms simpler than the definition in this book. Linear motion is basically motion that happens in a straight line. The word linear comes from the word line. It's also worthy to note that a one-dimensional motion is also linear motion. One-dimensional motion means straight line motion. Section 1.2, a conceptual description of motion. We have a test to your understanding that I would like you to pause and give it a try. On each diagram, draw at least 5 dots for position showing velocity on each dot and arrows for delta v, which is the change in velocity between the dots if necessary. Make your diagram fit the description. Now, what we need, of course, to begin this is we need a common reference frame. It was suggested in class, and I would highly suggest that we all kind of adhere to this together, that we use a common reference frame that uses going to the right positive, left negative, up positive, down negative, forward positive, backward negative. So right, up, and forward are positive in this common reference frame that we can all use together, and left, down, and backward are all negative. Let's begin. An object moves slowly at a constant speed to the right. Now for this, you're going to want to place, again, dots on the diagram, at least 5 for the position. And you want to place little arrows for the velocity and the delta velocity. Couple of things to note. When an object is speeding up, going in a positive direction, in other words, speeding up going right up forward. So RUF, R-U-F, stands for right up forward. Those are the positive directions in our common reference frame. Then what we have is a situation where we have a positive change in velocity, okay, because we're speeding up. But what we have is, if we're going in a positive direction, the velocity is going to be positive. Now, one thing to note, that triangle, remember, is the Greek letter delta, and it means change in something. So delta V means change in velocity. So if we're speeding up, going in a direction that is left, down, backward, that would be a negative change in velocity. Because the directional change. Slowing down, going right up forward, that's also a negative change in velocity. And finally, slowing down, but going left, down, backward. So those are 4 possibilities in which you have speeding up, slowing down, combined with a direction. And it influences the nature of the change in velocity. And the way it works is, anytime you're speeding up, the vector, remember, velocity is a vector, okay? So we're going to draw arrows for the vector for velocity and delta velocity, okay? Velocity and acceleration. And just to note, I know we haven't gotten to it yet, it's kind of an early preview, but acceleration is the change in velocity over time. Remember, ladies and gentlemen, these are both vector quantities. When an object is speeding up, the velocity, which I'm going to put in black, and the change in velocity are going to put in blue, are going to be in the same direction. But first, let's take care of the velocities. Velocity has to do with direction. So if it's to the right, I put V to the right. If it's left, I put V to the left, and so on. So you can see the direction of my velocity is in black. But if I'm speeding up, then my change in velocity, which relates to my acceleration, points the same way. Notice if I'm speeding up, that's got to point that way. So let's take a look at the first scenario. An object moves slowly at a constant speed to the right. Again, we want to make some dots at various points to represent this motion. Now, if we're talking about constant speed, then the dots we're going to be writing are going to be evenly spaced apart. Remember, acceleration refers to a change in velocity over time. So when we're referring to delta v, we're really applying, this is really reflecting on the acceleration of the object. So if an object moves slowly, what that means is we're going to have our dots pretty close together. It means we're not going to be changing our displacement, or our position is not going to be changing very much over the same time intervals. Okay, so we're going to use short velocity vectors. Each dot is going to have a short velocity vector, and they're all going to have the same length because we're talking constant speed. And they'll all be directed to the right since we were told it's going to the right. Now, since it's constant, delta v is going to be 0, because constant speed means there's no acceleration. Notice I'm making the dots and the arrows all the same length, evenly spaced apart. Again, since we're moving with constant speed, we're going to show no delta v arrows in this problem since we don't need to. There's no acceleration. Now, in the next scenario, it says an object moves quickly at a constant speed to the left. So since we're moving to the left, we should have longer velocity vectors, because more quickly means faster rate, longer velocity. Constant speed, we should have evenly spaced velocity vectors, and they should all be pointing to the left. Since we're moving with a constant speed yet again, we should have no change in velocity this time. So you can see all of my dots evenly spaced. I made them really long this time. They're all pointing left, and they're all evenly spaced and equal length. The next scenario says an object moves to the right while speeding up. Well, if you're speeding up, then delta v has to point to the right. Okay, why is this? Because we're told the object moves to the right, and if you're speeding up, delta v and v have to point the same way. So since we're speeding up, you want the dots to be placed farther and farther apart on the motion diagram, and the velocity vectors should increase in length throughout the diagram. So it can look something like this. Start with a dot over here towards the beginning, and then we can go a couple marks over, make another dot, and then space it out a little farther, make another dot, maybe about right here, and then keep spacing it out. Okay, now you can see with my 5 dots here, and I put the arrows in here to show the increasing velocity. You see the velocity vectors are getting longer and longer as the motion diagram continues. That's pointing to the speeding up nature, the acceleration nature. Finally, in this last scenario, an object moves to the left while slowing down. Now, for moving to the left, our velocity vectors need to be drawn to the left. But if we're slowing down, then your velocity vectors, your motion dots, your positions are going to get closer and closer together. And the arrows connecting these dots, or not connecting these dots, the arrows between these dots representing the velocities are going to get shorter and shorter. So as opposed to the previous scenario where your velocity vectors are getting longer and longer to reflect speeding up, now you can see they're getting shorter and shorter each time, eventually arriving at 0, assuming we're slowing down to a stop. Now, since we are slowing down, delta v has to be opposite the velocity vector, and you can see it's pointing to the right, which we already acknowledged as a positive reference frame direction. Therefore, although velocity is negative, delta v, or in this case acceleration, what delta v relates to, would be positive. Explain how delta v compares to the direction of v when an object is speeding up and when it is slowing down. So we already kind of stated this in the diagram, but let's summarize it here so that we can kind of use it as we need it. Basically, it is this. When an object speeds up, v and delta v point the same way. Now, when an object moves at a constant velocity, then that means there is no change in velocity. That means, of course, delta v is 0. When an object slows down, well, that is when v and delta v will point in opposite directions, like we saw in the last scenario. Section 1.3, Quantities for Describing Motion. Explain the differences between time and time interval. What time is your physics class? What time interval does your physics class cover? Time is the reading on a clock or a stopwatch. It's an instantaneous moment. A time interval, however, is what's called an elapsed time. It's basically the time between two separate clock readings or two separate points on a stopwatch. We could call those two separate times initial time and final time. Now, in terms of variables and in terms of symbols, we can use plain old t for a clock reading time at any particular moment we're looking at. And you could use delta t for a time interval. Again, remember, delta, the Greek letter delta, means change in something. So if you put delta in front of t, then delta t refers to the change in time. Now, I will tell you, there's times where delta t and t can just be used interchangeably, and I'll explain that more in class. Explain position. What is your position now? Position is where an object is located. It's a location of something. Your position right now is probably in a chair somewhere. we will use the variables x or y to represent a position. X is typically used for a horizontal position, and y is typically used for a vertical position. Both have the unit of meters. Explain displacement without using the word vector. Displacement is a change in position. Symbolically, it is delta x. Final position minus initial position. But you can also think of it as a straight line from start to finish. Explain path length. Note, in AP Physics, the word distance always refers to and means path length. Path length is simply just the total distance or the total length traveled. Path length has no direction. It's simply the distance between any 2 points. It's the length between any 2 points. In a path, hence the word path length. Answer these 2 questions. If the answer is yes, explain under what circumstance. If the answer is no, explain why not. Can displacement be negative? Well, the answer to that is yes. Displacement can be negative, but let's see why first. First, we need to establish a reference frame. Recall that a reference frame requires 4 things, okay? 3 things, rather. 1, you need to have some starting origin point. You need to start at some origin, wherever that beginning of the problem is. 2, you need to have coordinate axes that define a positive and negative direction. And there needs to be some unifying way of saying that all positive directions go one way, all negative directions go the other way. And 3, there needs to be some way of measuring time. Recall, we adopted a common reference frame that suggests going to the right and up are positive, left down are negative. In other words, the positive directions we established were going to the right, going up, and going forward. And as an abbreviation, I just call that RUF. RUF is positive. Negative directions we established were going to the left, going down, and going backward. So RUF is considered positive. LDB, according to our common reference frame, is considered negative. So Again, can displacement be negative? Well, yes, it can be negative. Displacement can be negative if the change in position is pointing in a negative direction. Can distance be negative? Well, no. Distance can never be negative. Remember, distance is the path length between any 2 points. And since distance measures path length, and length is always positive, distance must therefore always be positive. Section 1.4, representing motion with data tables and graphs. Again, with this test your understanding, you want to translate each of the motion diagrams into position versus time graphs. Do the best you can, and then pause the video, give it a try, and then resume the video to see how well you were able to make the graph. Okay, let's take a look and check with what you did and make any corrections if necessary. You can see, according to the motion map in this first scenario, that you have an object at what appears to be 5 meters. Oh, well, one thing we should also is assume the position, assume each position change is over 1 second. That is going to be key to these particular problems, is that every single position change happens every second. That'll easily tell you where to plot the point. You're plotting one point at 0, at 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. So you can see, ladies and gentlemen, the first plot point here would be at what, 5 meters? So at 0 seconds, we're at 5 meters. At 1 second, we're at 7 meters. At 2 seconds, we're at 9 meters. At 3 seconds, we're at 11 meters. At 4 seconds, we're at 13 meters. And at 5 seconds, we're at 15 meters. Draw a best fit line, of course, through that, and we can see the constant velocity motion sloped upwards. Now, for this next scenario, we kind of have something similar, except if we have 0 on the far left, 10, and then 20 on the far right, you can see that the motion map is going backwards from 19 to 16 to 13 to 10 to 7 to 4. And so we're essentially plotting those positions at each of the respective times. So we start at 19, and then make a dot at 16, then make a dot at 13, then make a dot at 10, then make a dot at 7, and then finally we'll make a dot at 4 seconds. And then go ahead and draw a best fit line through those data points. And we're looking at constant velocity, but notice if it's constant velocity directed to the left, notice that's a downward slope. That's a negative slope. I made an error on this, so I'm just recorrecting. Yeah, there we go. So that should be at 16. That's at 13. That's at 10. That's at 7. There we go. And that's at 4. Now it lines up pretty linear. So once you do that, go ahead and draw a nice best fit line through that, and you can see the downward slope represents the negative constant velocity. Now, in the following two scenarios, you want to translate each of the following into motion maps. So from position time diagrams to motion maps. Well, here you can see we're starting at 20 meters and we're ending at 10 meters, right, over 5 seconds. So we want to put those 5 dots starting at 20, and then you can see at 1 second we're at what, 18, then at 2 seconds we're at 16, then at 3 seconds we're at 14, and then at 4 seconds we're at 12, and then finally at 5 seconds we're at 10. And so go ahead and make those dots between 20 and 10 on the scale, and then give little short velocity vectors all directed to the left. Constant velocity, the arrows are all the same length. Constant velocity is shown on that picture as a downward constant slope as well. Now in the last scenario here, we're starting at 0 and we're ending at 20 at 5 seconds. This is also showing you constant velocity because it's a constant slope on a position time graph. However, it's a steeper line. So we expect our velocity vectors to be just slightly longer. And you can see at 1 second we are at, where are we at? We're at 4 meters. At 2 seconds we're at 8. So yeah, every single second we're increasing by 4 meters. So at 3 seconds we're at 12, at 4 seconds we're at 15, and then finally at 5 seconds we're at 20. So 16, not 15, and then 20. And you can see we have our 5 arrows are spaced out and a little bit longer. Section 1.5, constant velocity and linear motion. What is the basic equation that defines velocity? Well, first of all, if it's average velocity, we're going to put a v bar over the top. But for now, let's talk about velocity in general. Velocity is the displacement over time. It's the change in position over the change in time. Let's make sure we note what these variables are. So velocity is the letter v. Delta x is displacement. Remember, velocity is in a unit of meters per second. Displacement is also a change in position. And that's in meters. And then delta t, right? Delta t would be in, that's the time interval that happens in the problem, and that would be in seconds. Now, many times delta t can be used interchangeably with t, and I'll explain why that is in class. What is the position equation for constant velocity linear motion? Okay, and well, first of all, we're going to solve it for x, but basically if we take the equation above, v equals delta x over delta t, we get delta x is equal to v times delta t, or distance equals velocity times time, or displacement equals velocity times time. In this test your understanding, it says a person stands 10 meters away from a flagpole for 2 seconds. If the person's speed is 5 meters, 10 meters divided by 2 seconds. Explain why or why not. Well, the person is standing, so their position, their change in position is 0. Their displacement is 0. If their displacement is 0, their velocity has to be 0. It doesn't matter the fact that it happens over 2 seconds. Therefore, 0 divided by 2, the velocity is 0. Their speed is also 0 because there's no change in path length either. They're stuck in the same spot. Okay, since there's no change in length or change in position, there's not going to be a speed, nor is there going to be a velocity. In this next test your understanding, remember to pause it and try yourself. But it says a driver started from downtown Dallas and drives north on US 75 Central Expressway. The driver is 120 miles from Dallas at 2 p.m. Is the driver's speed 60 miles per hour? In other words, 120 divided by 2. Explain why or why not. Well, the answer is no, okay? And this is simply because nowhere in the problem does it mention that the time interval is 2 hours. That was something that was just, I guess, wrongfully deduced. 2 p.m. is just a clock reading. That is the clock reading. We were not told that the driver goes from 2 p.m. to, let's say, 4 p.m. That would be a 2-hour time interval. So since we're not given a time interval, no, you really can't figure out what their speed is at that point. How do you find displacement from a velocity graph? Well, ladies and gentlemen, displacement is the area under a velocity graph. More specifically, it's the area bound between the velocity graph and the t-axis. But for simplicity, we can just say for now, it's the area under a velocity versus time graph. In the following section, we have 4 objects that are moving during a 5-second interval of time to the, you have velocity time graphs. We want to rank them in terms of their forward displacements from highest to lowest. We're going to put a greater than sign between 2 unequal displacements and then an equal sign between any displacements that might be equal. Then perform the same ranking, but we're going to rank the distances as well. So first we're going to rank the displacements from forward to most backward, and then we're going to rank the distance from longest distance to shortest distance. First we're going to rank displacement. Then we'll rank the distance. Now, if you look, remember what we established, the displacement is the area under. So we just need to break this up into smaller rectangles. The first rectangle has a height of 10 and a base of 2. So in other words, we have a displacement of 20 meters. 10 meters per second times 2 seconds is 20 meters. Then for the smaller rectangle here from 2 to 4 seconds, well, it has a height of 5 and a base of 2, so that would be 10 meters. Add that together, and we have a total displacement, delta x, of 30 meters. Well, in the second object B, we have a base of 4 for the graph and a height of 5, which gives us a displacement, delta x, of 20 meters. In object C, we can see that from 2 to 4 seconds we have a positive area, and from 0 to 2 seconds we have a negative area that I'm denoting in black and blue. So any area that's taken above the t-axis is considered positive displacement. So that would be positive 2 times 10 or positive 20. And the blue area would be the area taken below the t-axis. That would be negative area or negative displacement. So if we add them up, a positive 20 plus a negative 20 adds up to 0. And for object D, we have a negative area below the t-axis for 4 seconds. It has a height of 10 and a base of 4, which means we have a displacement of negative delta x is negative 40 meters. Now let's figure out the distances. Well, in the first situation, object A, the distance is also going to be 30 meters because it's simply 10 plus 20 and it's all positive. And same thing with object B, since the displacement is in the positive direction, it's also 20. But for object C, I mean, you've got 20 going one way plus 20 going the other way, and distance shows no direction. Therefore, 20 plus 20 is actually a total distance of 40 meters if we don't account for direction. And similarly, since distance does not account for direction, then object D would also be a positive 40 meters. So ranking these, of course, from most forward displacement to most backward displacement, the highest displacement would be A. So let's write that first, then a greater than sign. So A is greater than B, because you can see it's 30, then it's 20 for delta x, and then it's 0. The next highest delta x is 0 for C, and then the most negative or most backward displacement is negative 40, which is D. So A is greater than B is greater than C is greater than D in terms of most forward to most backward. Now, in terms of distance, C and D are both the same length, so we'll write C equal to D because they're both equal to 40. But both of those are greater than A, which is 30, which is greater than B, which is 20. Now, for these examples here, go ahead and skip them for the time being, as we will conduct these examples and practice them together in class. Section 1.6, motion at constant acceleration. In simple everyday language, explain the difference between average velocity and instantaneous velocity. Well, average velocity, ladies and gentlemen, is the average over an entire time interval. It's taking the entire displacement divided by the entire time. Instantaneous velocity, however, is the velocity at one moment in time. It's a snapshot, if you will, of one particular moment. What does a speedometer measure? Well, speedometer measures instantaneous speed. And why is this? Well, it turns out that speedometers display the instantaneous speed of any vehicle. Why is it the instantaneous speed and not the instantaneous velocity? Because speedometers do not measure the direction in which you are going. They simply measure the rate of your travel, how fast you're going. Again, remember to pause these test your understandings and give them a try, type or write out an answer, and then resume the video to see if you're correct or any corrections that need to be made. What two instruments in a car can be used to measure the average speed during a long trip? Explain how these instruments can be used to calculate speed. Pause your video and try this. All right, let's see what you came up with. Average speed is calculated as total distance divided by the total time. Now, what instruments in your car could you use to measure total distance and total time? Well, you can use to measure total distance this device called the odometer. The odometer displays the miles that you've traveled. Or there's some things in car called trip meters where you can start from 0 and see how many miles you've driven. But basically, an odometer would be there to measure the distance. The clock display would be something that could be used to measure the time interval, because you would measure the time interval between two different points on a clock display. And odometer reading divided by the time interval would, of course, be the average speed. Again, if the next test your understanding, please try it, pause the video, and check and see if you're correct or if any corrections need to be made. A police officer pulls over a motorist and states the motorist was going faster than the highway speed limit. The motorist states that the speed limit is 60 miles per hour. Then he left home at 4 p.m., that he traveled 120 miles, and that is exactly 6 p.m. right now. The officer still gave the motorist a ticket, and the charge still held up in court. In a brief paragraph, explain the argument the motorist was making in your own words, and explain what argument the officer made in court that caused the charge to hold up. Okay, let's see what you guys put. For this, the motorist was arguing that their average speed, well, remember how average speed is calculated. Average speed is total distance over total time, right? So, the motorist was arguing that their average speed was over the entire 120-mile distance, which that part was true. However, what's not true is that it wasn't a constant 60 miles per hour the whole time. So, in other words, average speed, if we consider this to be an average speed like the motorist said, then we take 120 miles and we divide 120 miles by 2 hours. And if we do that, we get an average speed of 60 miles per hour. But then again, that's just an average speed. The police officer argued that the instantaneous speed could have been greater than 60 miles an hour any point in the journey. And so, as we can see, the motorist was using an average speed argument for their description. 120 miles divided by 2 hours is 60 miles per hour. But again, that's on average. The instantaneous speeds could be higher and lower than that average due to various traffic conditions. So since this instantaneous speed could very well have been greater than 60 miles per hour, it is possible that the officer could have used a radar gun to record this instantaneous speed that was indeed greater than 60 miles per hour. We're going to skip the frame of reference page, scroll along to section 1.6, motion at constant acceleration. Write a word equation for acceleration. Acceleration is the rate of change of velocity. Write an equation for the average acceleration. Well, average acceleration is a with a bar over the top of it, so a bar. And it's equal to the change in velocity over the change in time. Change in velocity we can write as v minus v naught. Remember, the little subscript 0 stands for naught, N-A-U-G-H-T. Refers to initial quantities. Let's label all of our variables here so we get a handle on what we're working with here. A is acceleration in meters per second. Actually, meters per second squared. We'll talk about where we get meters per second squared shortly. V is the final velocity in the problem, measured in meters per second. V naught, the V sub 0 is pronounced V naught. That's the initial velocity or the starting velocity in the problem, also measured in meters per second. T is time, but T is specifically the final clock reading or the final time, measured in seconds. And T naught is the initial time, also measured in seconds. Since the initial clock reading usually starts at 0, then the final time minus 0 means that delta T and T can oftentimes be used interchangeably. Don't forget delta T is our time interval, but delta T and T can be used interchangeably if the beginning clock reading time is indeed 0. Again, for an average acceleration, we want to put a bar over the A bar. Now, when we talk about the difference between average acceleration and constant acceleration means constantly increasing or decreasing your change in velocity over a particular time interval. And if we average constant values, we get the same thing. Now, for average to become instantaneous acceleration, what happens to our equation? Well, basically, we have to take this thing called limit as delta t approaches 0 of delta v over delta t. But see, ladies and gentlemen, that's a calculus application, and we're not doing calculus in this class, so don't worry about that. However, we can find the instantaneous acceleration by finding the slope of the tangent line of the velocity versus time graph. And that'll be how we do that in this class. The slope of a position graph is the velocity. The slope of a velocity graph is acceleration. So what is the symbol for acceleration? Well, that's A. The unit for acceleration is going to be meters per second squared. Now, explain where the square comes from in the units. Well, delta V over delta T can be written as meters per second over second, which is the same as meters per second over seconds over 1. And so if you flip that, it's meters per second times 1 over second. And that gives you meters per second squared. What does a velocity versus time graph look like for an object that experiences constant acceleration? What features of a velocity time graph can be used to determine the acceleration? Well, constant acceleration, which we're going to abbreviate as CA, constant velocity we abbreviate as CV, constant acceleration we abbreviate as CA. Constant acceleration is going to, on a velocity versus time graph, look like a sloped up or down line. So it's going to be a straight line, either sloped up or down. If it's sloped up, it's positive constant acceleration. If it's sloped down, it's negative constant acceleration. This is on a velocity time graph again, mind you. Again, why is this? Because acceleration is the slope on a velocity graph. Now, since acceleration is the slope of a velocity graph, and we established that constant acceleration looks like a straight line sloped up and down, what this means is we are constantly accelerating, and something that is constantly accelerating, constant acceleration, should have a constant slope. Therefore, straight line. Now we're going to get into our constant acceleration equations. What is an equation that expresses change in velocity as a function of time? Well, it is written as v equals v naught plus a times t. Let's identify all the variables and their respective units. V is the final velocity, measured in meters per second. V naught is the initial velocity, measured in meters per second. A is the acceleration. Measured in meters per second squared. Remember, that's the unusual unit, right? And t is time, measured in seconds. Well, how do the directions of acceleration and velocity determine whether objects speed up or slow down? Use the TIP box and write a brief set of rules for how A and V are directed when objects speed up or slow down. Okay, so what we can do is we can make ourselves a graphic organizer to really organize all the possibilities for not only speeding up and slowing down, but the direction in which way an object is going, and use those both to categorize constant acceleration as positive and negative. So first, let's talk about the positive directions and the negative directions. We'll put them across the top of the chart. Positive directions, remember, were right, up, and forward. According to our common reference frame, negative directions were left, down, and backward. Now, that would be the directional side of acceleration. The change in velocity side of acceleration, it would be a speeding up, which would be considered positive, delta V, and slowing down, which would be considered negative. To get the overall feeling of constant acceleration, you have to combine each row with each column. You have to combine speeding up or slowing down with the directional change. So if we're speeding up in a positive direction, two positives mean we have an overall positive constant acceleration. If we're speeding up in the negative direction, however, the one negative kind of overrules everything, and we have an overall negative constant acceleration. If we're slowing down in the positive direction, again, we have a negative constant acceleration. And if we're slowing down in the negative direction, well, those two negatives kind of combine to give you a positive constant acceleration. Now, let's see why when we look at how we can combine velocity and acceleration together. So let's talk about speeding but in a positive direction. So if we're in a positive direction, that means we direct the velocity vector to the right. And if we're speeding, the acceleration vector points the same way. So A and V point the same way, both to the right. Since A is pointing to the right, that's positive constant acceleration. Now what about speeding in some negative direction, like left, down, or backward? Well, if you're going in the negative direction, you now need to have a velocity vector directed left. Since you're speeding, your acceleration has to be pointing the same way, so acceleration is also pointing to the left. And since acceleration is pointing to the left, we have a negative constant acceleration. Let's say we have slowing, but in a positive direction. Now, if we're going in the positive direction, that of course has a velocity vector directed to the right. But since we're slowing, the acceleration vector is always opposite the velocity vector. So the acceleration vector is now pointing to the left. And since it's pointing to the left, that would be negative constant acceleration. And lastly, let's examine slowing in a negative direction. Why did those two negatives give a positive constant acceleration? Well, if you're going in the negative direction, we have negative velocity going to the left. But since we're slowing, the acceleration must oppose the direction of velocity, and acceleration must point to the right. Any acceleration pointing to the right would be positive constant acceleration. Pause the video and fill out the following parts, and then resume the video to see how well you did. Okay, let's take a look and see how you did. A car's acceleration is 5 meters per second. That means the car's velocity increases by 5 meters per second every second of time. Second, a car is advertised to go from 0 to 60 in 4 seconds. While this is the car's velocity increased by 60 meters per second every 4 seconds. Every 4 seconds of time. The overall acceleration of the car's acceleration would be 15, 60 divided by 4 meters per second squared. And in the third scenario, we have the acceleration of an object is 10 meters per second squared. The penny dropped from the top of the Empire State Building. The pennies, and keep in mind, 10 meters per second squared is what's referred to as the acceleration due to gravity. And for the acceleration due to gravity, we use the symbol lowercase g. So the acceleration of the object is that. The penny drops from the Empire State Building. The penny's velocity increases by 10 meters per second each second of time. Okay, write 2 almost identical sentences using the word rate of change of. Well, again, pause. Okay, now resume. Let's see what you wrote. Velocity is the rate of change of position. And its equation that that matches that. Remember, the word rate refers to dividing by time. So velocity is position over change in position over change in time. Acceleration would be the rate of change of velocity. And that's how we get acceleration equals change in velocity over change in time. How is displacement found from a velocity time graph? Well, we actually worked this earlier in a test your understanding example. And if you recall, displacement is found by finding the area under a velocity time graph. And when I say area under, I mean the area bound between the graph and the t-axis. To look at it further and summarize, you can have essentially, if 0 is the t-axis, velocity equals 0 is the t-axis, any areas that are above the t-axis are considered positive areas, and they relate to positive displacements or positive delta x's. Any areas that are below the t-axis, well, those are considered negative areas, and those are considered negative displacements or negative delta x's. Write an equation that relates an object's position as a function of time with constant acceleration. The equation is x equals x naught plus v naught t plus 1/2 a times t squared. Let's just move the equation over here. Identifying the parts, x is the final position of the object, the final location. In terms of problem solving, it represents how far. X naught is the initial position, also measured in meters. V naught is the initial velocity, measured in meters per second. A is the acceleration, the constant acceleration, measured in meters per second squared. And t is again time, measured in seconds. Now, let's examine the graph and the shapes of position time graphs. What shape does a position time graph have when an object undergoes constant acceleration? Well, the flat answer to that, the quick answer to that is that the shape is going to be a curve. And you have 4 possible curves you can make. We can slope up, concave up. We can slope down, concave down. Or we can go concave up or down from other starting positions that are not 0. We could start at some position, and then come back to 0, concave down, or start at some position and kind of come back to 0, sort of concave up, like that. So you have 4 possible ways that you could really, see something, either starting from a position of 0 or not 0. Now, we can break down the slope of this, the changing slope of this, from essentially looking at the slope as it relates to a flat slope or a steep slope. Because remember, acceleration is a change in velocity, and the slope of a position time graph is the velocity. So when we go from a flat slope, which is essentially 0 velocity, to a steep slope, which is a higher velocity, we're speeding up in the positive direction, which is constant acceleration. When we go from a steeper slope in the beginning of the curve to a flatter slope, that means we're slowing down. We're decreasing our velocity. But all of the slopes are positive, so we're slowing down in the positive direction. Since slowing is a negative value or a negative attribute, we have an overall negative constant acceleration. Now, if we are going from flat to steep, a flat slope to a steep slope, we are increasing our velocity, but we're doing so in a negative way. So we're increasing our velocity, we're speeding up, but we're speeding up in a negative direction. So if we're speeding up in a negative direction, that's an overall negative constant acceleration. And lastly, if our curve is going from steep to flat, that means we're going from a faster slope to a slower one, okay, or to a zero slope. We're slowing down. Steep to flat, we're slowing down. But we're slowing down with negative slope, so it's a negative direction. Those two negatives combine to give you an overall positive constant acceleration. What is the third alternate equation for constant acceleration motion? We call it the no time equation because time does not appear in the equation. And it is v squared equals v naught squared plus 2a times the quantity of x minus x naught. Let's examine the variables. V, where it's v squared, the actual variable v is final velocity again. And again, that's measured in meters per second. Where it says v naught squared, the actual variable is v naught. Remember, that stands for initial velocity. And that's in meters per second also. A is acceleration, meters per second squared. X represents the final position. Final position is how far something went. That is measured in meters. And x naught is the initial position, also measured in meters. One thing to note about the initial position, we are always going to assume the initial position is 0 unless the problem tells us otherwise. Now we do have a fourth constant acceleration motion equation that we can write down. And the fourth equation is one that we can use when we're not given acceleration. And it's essentially delta x equals average velocity times time. But we write average velocity as v plus v naught over 2 times time. Again, we use this when we have a change in velocity in time, but we're not given the actual acceleration variable. We're not given a. So it's a fourth equation that can be used. All right, in this next test your understanding, we have 4 objects that are moving during a 4-second interval of time according to a velocity versus time graph. Rank the object in terms of acceleration and displacement during this time. Well, it's better to make calculations for these things and then examine the ranking of your calculations. So what are we actually calculating here? Recall, acceleration is the slope of velocity time graphs. So we're going to have to find the slope of each graph to rank the accelerations. But also recall that displacement, which is delta x, is the area under a velocity time graph, or the area bound between the graph and the t-axis. In black, I'll be calculating the accelerations and the positive displacements. And in blue, I'll be calculating the displacements and the negative areas, negative displacements. So let's take a look at the slope here. Well, the slope for this first object A can be found by going either up 10 over 2 or up 20 over 4. Either way, we get a constant slope of 5 meters per second squared. The displacement, on the other hand, we have 2 triangular regions. From 2 to 4 seconds is a positive displacement. Now it's the base is 2, the height is 10, 2 times 10 is 20, take half because it's a triangle. We're looking at a displacement of positive 10 meters. And then the negative displacement below the t-axis, right, is a base of 2, height of 10, 2 times 10 is 20, take half is negative 10. So our displacement is actually going to be negative 10 plus 10, or 0. So again, positive areas are positive displacement, negative areas are negative displacement. And when the two areas equal each other above and below the t-axis, you know they're going to end up canceling to 0 displacement. You can think of it as though a person is walking backward for 2 seconds, and then immediately from 2 to 4 seconds walking forward and ending up in the same spot they started with. And if they start and end at the same location, the change in position is 0, therefore the overall displacement ended up being 0. Now for object B, that one's pretty straightforward. The velocity is a straight slope, horizontal constant. The slope is 0, therefore the acceleration is 0. We're moving with constant velocity of 10 meters per second. The displacement is also fairly straightforward to find because the area is a nice rectangular region with a base of 4 and a height of 10, therefore the displacement is 40. Now, just like object A, object C is going to have a slope of a line, and we can find that by either going down 5 and over 2 or down 10 and over 4. Either way, we get a negative slope, so a negative acceleration, and it's negative 2.5 meters per second squared. Since we have positive and negative triangular area regions, let's figure them out. Area is 1/2 the base times the height, so positive 5 meters, right? And then below the axis is equaling negative 5 meters. Therefore, the displacement delta x has to be 5 plus a negative 5, or 0, just like we saw in object A. In object D, well, let's see, we have a slope that would rise 10 and over 4. That would be positive slope, so it's a positive 2.5 meters per second squared. The displacement, right, is the triangular region negative of the underneath the t-axis. It's a base of 4 and a height of 10. 4 times 10 is 40. Take half is 20. But since it's a negative area below the t-axis, it's a displacement of negative 20. Okay, we need to rank most forward acceleration with most backward acceleration. So most forward acceleration would be the most positive acceleration. Most backward acceleration would be the most negative acceleration. So A has an acceleration of 5, that's the highest. Then D, because it goes from 5 to 2.5. Then B, which is 0. Then C, which is negative 2.5. So put the greater than symbols in there. So A is greater than D, is greater than B, is greater than C, is the lowest, or most negative, or most backward acceleration. In terms of displacement, the most forward displacement would be B at delta x equals 40. The next one would be A at 0. But A and C are both 0, so we can say B is greater than A, which is equal to C. And both of them are greater than the negative displacement shown in D of negative 20.